So welcome to this session about hacking with Unicode. So I'm Mathias, as you've heard by now. I work for Opera Software in developer relations, and my job kind of requires me to have a certain knowledge when it comes to web standards, so HTML, CSS, and JavaScript. I kind of need to know about a couple of weird edge cases involving these standards and how browsers interpret them. And for a very long time, I was doing research on all this stuff just for fun. But over the years, I realized that there's a bit of an overlap between this sort of knowledge and the kind of knowledge that a hacker needs if they want to attack a web application. So today I'm going to talk about a couple of things that I learned about Unicode over the years. First, I'll briefly explain the basics of Unicode and character encodings, just to make sure we're all on the same page. Then we'll take a look at how JavaScript handles Unicode and what kind of bugs that this often leads to. And then we'll do the same thing for the MySQL database software. And finally, I'll demonstrate how this knowledge can be used to actually craft exploits. Okay, so let's get started by taking a quick look at the very basics of Unicode. The first thing to remember about Unicode is that it is not an encoding. People very often confuse UTF-8 for Unicode, but they're really two quite different things. Unicode is not an encoding. It's more like a database that maps any symbol that you can think of to a unique number for that symbol called the code point. Any symbol also gets assigned a unique name for that symbol, and the main purpose for that is that this way you can refer to any symbol at all without having to use the symbol itself. You can just refer to the code point, the number, or the name for the symbol, and everyone will know exactly which symbol you're looking for. So, for example, Unicode maps the Latin capital letter A to the code point U+0041. And this is a hexadecimal number, not a decimal number, and the code points are usually formatted this way. So hex digits, usually 0 padded up to at least 4 hexadecimal digits, and they get the U+ prefix. Now, another example of a code point and of a character is the Latin small letter a. It's a completely different character, so it gets its own unique name and its own unique code point. This is how Unicode works. So there's a lot of different symbols in Unicode, and each of them have their own code point. There's a lot of weird stuff, like there's a snowman, and lately there's been a lot of emoji additions to Unicode as well, like there's the pile of poo, for example. And as you can see, the code point is 1F4A9 in this case, which consists of 5 hexadecimal digits. So at this point, you may be wondering what the highest possible code point value is, or how many code points are there in total in Unicode. Well, the answer is Unicode ranges from O to 10FFFF. That's a little over 1.1 million possible code points and symbols. Now, to keep things a little bit organized, Unicode divides this huge range of code points into 17 planes, which consist of about 65,000 code points each. And the very first of these planes is probably the most important one. It's called the Basic Multilingual Plane, or the BMP, and it contains all the most commonly used symbols. In fact, whenever you're writing a text document in English or even German with all your weird umlauts and characters like that, you probably won't even need any code points outside of this BMP. So because this basic multilingual plane contains all the most popular symbols, I like to refer to it as the notorious BMP. Anyway, just like any other plane, it consists about 65,000 symbols in total. So that leaves us about 1 million other Unicode code points that live outside of this BMP. And the planes that these code points belong to are called supplementary planes, or the astral planes. So astral code points are pretty easy to recognize because you need at least 5 hexadecimal digits to represent them. Okay, and that includes our very basic introduction to Unicode. Now let's talk about character encodings for Unicode. So here's a list of encodings that fully support Unicode. This means that they can encode and decode any Unicode code point value in that entire range that we just talked about. So this table shows the number of bytes that each encoding requires per code point. Now, one of the encodings, as you can see, is a fixed width encoding. It's UTF-32, and it uses 4 bytes for any code point whatsoever. It doesn't care what code point it is. It always needs exactly 4 bytes to represent it. So that's nice and simple, perhaps, but it's not very efficient in terms of storage space. There are other solutions like variable width encodings, like UTF-16, for example. It uses exactly 2 bytes for BMP symbols, but 4 bytes to encode an astral symbol. Now, whenever you have the choice, you should always go for UTF-8, and there are several reasons for that. For starters, it supports full Unicode, just like all the other encodings you see here, but it's also very much optimized for storage. The most commonly used symbols take up fewer bytes. As you can see, BMP symbols take 1, 2, or 3 bytes, but if you just look at ASCII symbols only, they will always only take up a single byte. So it's very much optimized. And because of that, it's also fully backwards compatible with ASCII. This means that any existing ASCII document out there is automatically a valid UTF-8 document. Okay, so the next part of this talk will be a little bit in-depth. We'll talk about various problems involving Unicode, specifically in JavaScript, and common mistakes made by JavaScript developers and how they can be fixed. But even though this section is about JavaScript, other programming languages will have similar problems, so don't get too hung up on the language-specific details here. Instead, try to think of the underlying problems, because that's really what it's about here. So for example, in string literals in JavaScript, you may have seen things like this before. It starts with a backslash followed by X followed by hexadecimal digits. And now that we know about Unicode, it's easy to see what these 2 hexadecimal digits refer to. They refer to a Unicode code point. So this is a way to use a character or a symbol in a string without having to use the symbol itself. You can just use an escape sequence for it instead. And this is useful if you want to use non-ASCII symbols, for example, but you want to make sure that your source code remains ASCII safe, like in this case. So this is fairly useful, but because you're just limited to 2 hexadecimal digits, there's not a lot of code points that you can use this for. Luckily, there's another type of escape sequence called the Unicode escape sequence, and it looks like this. It starts with a backslash followed by U, followed by 4 hexadecimal digits. So of course, this opens up a lot of other code points that we can now represent using an escape sequence as well. For example, the code point 2661, which is apparently the white heart symbol. So this is super useful, and because we have 4 hexadecimal digits, we can use this for any BMP code point at all. But what do we do about all those other Astral code points? We need more than 4 hexadecimal digits for those, right? Or another way to phrase the question would be, what about our friend, the pile of poo? And other equally important Astral symbols, of course. So how can we escape these symbols if we can only specify up to 4 hexadecimal digits at a time? The answer is, we kind of can, but it's a little bit complicated. Now in ECMAScript 6, the latest version of the JavaScript standard, it's in fact really easy, because there is yet another type of escape sequence. It starts with a backslash followed by U, followed by braces. And between the braces, you can use any amount of hexadecimal digits you want to represent the code point. Of course, you only need 6 to be able to represent all the Unicode code points out there. So this is a very easy way of including a symbol into a string without having to use the symbol itself. You just use the code point, and that's it. However, if you need something that works with legacy environments and with ECMAScript 5 environments, because ECMAScript 6 is still fairly new and it may not be around everywhere, you have to use this thing called surrogate pairs, and that's really unfortunate. In this case, each escape sequence represents the code point of 1/2 of the surrogate pair, and when these 2 halves are combined, they form a single Astral symbol. And this is confusing for a number of reasons. For starters, the code points that you see escaped there, they don't really look anything like the original code point that you were trying to represent. So just by reading this code, it's not immediately obvious that you were trying to represent 1F4A9 or the pile of poo. Now, there are formulas that you can use to calculate the surrogate pairs based on this Astral code point or the other way around. And here's a JavaScript implementation of those formulas. Now, you don't have to remember the exact formula, of course, but apparently JavaScript developers need to know that this is a thing and that this exists, and they need to be able to implement this if they want to deal with strings correctly in JavaScript. Now, the whole concept of using just a single escape sequence for BMP symbols, but 2 individual escape sequences for Astral symbols is very confusing, and it has its consequences throughout the entire language. For example, let's say you want to count the number of characters in a string in JavaScript. I would probably just use the length property of the string. Every string has one, so why not use it, right? And indeed, in these examples, the length property just happens to reflect the number of symbols in each string. But this is not always the case, and that was the first thing that really surprised me when I found out about this. So here we're using the code point 41, which is the Latin capital letter A, and the length of the string is 1. So let's try some other Unicode characters. Here we're using the mathematical bold capital letter A, which is a different symbol, so it gets its own code point, and in this case it happens to be an astral code point. And as a result, the length of this string now is 2 instead of 1, even though there's only a single symbol there. And the reason for that is because JavaScript apparently exposes each half of the surrogate pair as if it was a separate character, even though it's really not. So to us as human beings, that is really confusing because we generally think in terms of Unicode symbols or even visual graphemes. And JavaScript now kind of forces us to deal with these surrogate pairs, which is really an encoding detail. Now, similarly, if you try the string with the pile of poo in it, you get its length, the result is 2 instead of 1. And for the Americans out there, there's a very obvious joke to be made, but instead I'm going to show you a real-world example of where this actually breaks an application. So this is Twitter, not too long ago. As you know, they allow 140 characters per tweet, and their backend doesn't really care what kind of code points you use. If it's an astral code point or a BAP code point, it just counts as a single character, which is excellent. However, their JavaScript counter on the website just checked the length of the string, so they didn't account for these surrogate pairs. And because of that, for every astral symbol you entered, the counter would decrease in steps of 2 instead of 1. So because of this bug, you could only tweet 70 piles of poo at a time. It was really devastating. Now, another example is the Countable.js open source project. Literally all it does is add live paragraph, word, and character counting to your web pages. So it measures how many text you have input into an input field and then displays those numbers elsewhere on the page. So the first thing I did when I saw this demo page was, of course, to enter a pile of poo. And unsurprisingly, it counted it as 2 individual characters rather than 1. So these are just some examples. I'm not hating on Twitter or this open source project, but I'm just pointing out that this is a really obvious and honest mistake to make, and a lot of JavaScript developers just don't know about these issues. The problem is not that they don't want to fix this, because they fixed it right away when I reported it. The problem is that many people just don't know about these problems because they're so surprising. And in fact, this is kind of what it felt like to enter that pile of poo into that form, because I could always knew that something would go wrong, you know. It was kind of predictable. So getting back to our question, how can it be done? How can we accurately count the number of symbols in a JavaScript string? Well, one solution would be to use a third-party library that implements those formulas that I showed you earlier. And in this case, we can use Unicode UCS2 decode, which translates between JavaScript strings and Unicode code points. So if you then get the length of the resulting array of code points, you will get a more accurate result than before. Of course, this solution is far from ideal, because now you've introduced a dependency just to be able to count the number of code points in a string. It really shouldn't be that hard. And for that reason, in ECMAScript 6, they added some new features that allow us to do this without the use of any libraries at all. You can use array.from, pass in a string, and that will give you the same results. Or you could use the spread operator, which is also new in ECMAScript 6, and it also has the same result. Now, I've also made a tool that takes a string as input, and then it shows the escape sequences for any special characters within that string. So it's a bit similar to a hex dump, but in some cases it's more useful because the output is always valid JavaScript in this case. So with this tool, it's really easy to tell which symbols a string contains exactly, even if the symbols are non-printable or white space or other things like that. So now we know how to count code points properly in JavaScript, but if we're being really pedantic, then counting the number of symbols in a string is even more complicated. And of course, this really depends on your use case, but consider this scenario where JavaScript seems to be telling us that these two strings are different, although visually there is no real way to tell. So what is going on there? Well, I took these two strings and I copied them into the tool that I just showed you, and this is the output that I got. So the first string apparently contains the code point f1, which is the n character with the tilde on top of it. And the second string has a separate n character followed by the code point 0303, which is a combining tilde. Unicode has lots of these combining marks, and the way they work is they just get applied to the previous symbol. So if you look at it this way, it's obvious to see that these strings are actually different because they use different code points internally, but visually they look the same. And if we are counting the number of symbols in a string, we don't really care about the underlying encoding or code points that are being used. We just expect a result of 6 for both these strings. So how can we make that happen? Well, the answer is to use Unicode normalization. And this is another new feature in ECMAScript 6. You can just call normalize on any string, pass in the normalization form. In this case, we're using NFC, which takes care of these lookalike symbols for us. Of course, afterwards, we'll still have to take care of these astral symbols and surrogate pairs like we did before. And this gives us an even more accurate result than before. So is this solution absolutely perfect? Well, again, this really depends on your use case. If you have to support crazy stuff like this, where basically lots of combining marks are being applied to the same symbol over and over again, that's why it looks so weird, you'll have to do a little bit of more work. So in this case, I count 9 visual symbols, including the space in the middle there. But even our most pedantic function would count 116 symbols. And it's easy to see why, because there's a lot of code points in there. If you need to support this, you would have to use a regular expression that strips away all these special characters before you count the rest of the remaining characters. Now, one more example to make you think about all these underlying Unicode issues is reversing a string. It sounds pretty simple, right? And in fact, the common solution to the problem is you just take the string, split it up into an array of characters, reverse the array, and then glue it back together into a string. And that seems to work fine. If you reverse ABC, you get CBA. If you reverse mañana, where the N with the tilde is a single character, it still works fine. However, if you reverse the other mañana, where N and the tilde are 2 individual code points, now suddenly the tilde gets applied to the A character instead of to the N, which is not what you would expect. And finally, if you try to reverse an astral symbol, like the pile of poo, now we know that this consists of 2 surrogate halves in JavaScript, right? So you still have the surrogate pair, but now it's in the wrong order. So the reversed string won't even contain the original symbol anymore. This is a form of data loss. In other words, even something as seemingly simple as just reversing a string becomes really tricky if you need full Unicode support in JavaScript. Luckily for us, a brilliant computer scientist by the name of Missy Elliott came up with a bulletproof algorithm that accounts for these issues. And the algorithm goes, I put my thing down, flip it, and reverse it. And indeed, if you swap the position of any combining marks with the symbol they belong to, as well as reversing any surrogate pairs before further processing the string, all these issues are avoided successfully. So thank you, Missy. And there's actually an implementation of this algorithm in the name of asRever. So if you ever do need to reverse a string in JavaScript, feel free to use this library. It handles these cases perfectly. One more example is, let's say you want to iterate over a string and do something with each individual code point in the string. In ECMAScript 5, you would have to write a lot of boilerplate code just because of those surrogate halves. You will need to combine the surrogates and treat them as one single unit, and there's a lot of code that you need to write for that. Luckily, in ECMAScript 6, it became a lot easier, because now you can use for-off loops, which automatically deal with whole code points for you. But this is yet another example that shows how complicated the underlying JavaScript Unicode support is. These were just some examples. Literally everything involving strings before ECMAScript 6 is affected by this kind of behavior. So things like from character code, character add, substring, slice, anything that involves strings is affected by this. Oh, and there's also this thing called regular expressions. I have actually an entire separate presentation just on regular expressions and Unicode in JavaScript. So check that out if you're interested. But I think we can all agree that JavaScript has a Unicode problem. These are just some of the problems that JavaScript developers are facing. And from my experience, most developers just don't know about these issues at all. And that, of course, is an opportunity for penetration testers. So the main takeaway here is the pile of poo test. Whenever you're pen testing a JavaScript application, be sure to enter a pile of poo or any other astral symbol. In many cases, there will be a bug of some sort. And in some cases, you know, the bug might lead to a security-sensitive vulnerability. In other words, the pile of poo is the new null character. Now, before we move on to the actual exploits, let's talk about some of MySQL's problems. So let's say you want to create a MySQL database to store some text. So you know UTF-8 is the preferred character encoding, because I just told you. So you read some online tutorials, and you create a new table, and you set the default character set to UTF-8. OK, everything seems to work fine until you try to insert a string that contains an astral symbol. So the query doesn't fail, you don't get an error, it will just show a warning. But this means that most pieces of software on the web won't really detect this, because they have some error handling in place, but they don't really do anything with warnings. Now, the warning contains the UTF-8 encoded byte sequence for the pile of poo character, and it shows that the string value is somehow incorrect. So MySQL's default behavior in this case is a little bit weird, because instead of throwing an error, it still tries to insert the string into the database, and it just stops at the very first symbol that it cannot handle, in this case, the very first astral symbol. So effectively, the string is truncated at the first astral symbol that we use. This is a form of data loss, which is terrible in its own right, but it gets much worse. So it turns out that MySQL's UTF-8 character set only partially implements proper UTF-8 encoding. It can only store UTF-8 encoded symbols that take up 1 to 3 bytes, but not the 4 byte UTF-8 encoded characters like all the astral symbols. So if you need to use astral symbols in MySQL, you will have to use UTF-8 MB4 instead. And this is actual UTF-8, unlike what MySQL calls UTF-8. So if you insert an astral symbol or any other Unicode symbol into such a database, it will work fine, exactly the way you would expect it to. So always use UTF-8 MB4 instead of UTF-8 in MySQL. Okay, now we talked about Unicode, character encodings, we saw some common problems in JavaScript and MySQL, so let's see some examples of where people actually use this knowledge to actually exploit bugs. So remember when we talked about encodings before and I showed you that table with bytes for each encoding? Well, I told you to use UTF-8 whenever you have the choice because it can encode every possible Unicode code point. It's backwards compatible with ASCII, and it's optimized and compact, making it very useful for storage. Well, those were not the only reasons. Various other encodings turn out to have security issues when they're used with user-supplied content. UTF-16, for example. So this is a proof of concept made by Henry Sivonen, who works for Mozilla. So let's imagine that this is user-supplied content. There is some text on there, and there is some garbled encoding mismatch kind of text. And some social engineering is used to trick the user into changing the encoding for the page. And as soon as a victim does that, boom, a cross-site scripting vector applies. So what happened there? How did this happen? Well, let's take a look at the relevant part of the hex dump. It's right here. So the encoding table set UTF-16 uses 2 bytes for each BMP code point. So this means that this is the first code point that is relevant to our cross-site scripting attack. The code point will be 3C73, but as you can see on the right-hand side, if you were to decode this as ASCII and consider each individual byte as an individual character, you actually get the start bracket and the lowercase s character, which is the start of a element. Now, the next code point is this one, but again, in ASCII or in UTF-8, which is backwards compatible with ASCII, it is actually 2 characters, the C and the R. And it just goes on like that for another while until the whole cross-site scripting payload is completed. So this is why, if you're treating this document as UTF-16, you will get some garbled Chinese-looking text. But if you view it as ASCII or UTF-8 document, then it becomes a completely different document all of a sudden, and it suddenly contains a cross-site scripting payload. Okay, so this might seem like a little bit of a far-fetched vulnerability because it relies on social engineering. You need to trick the user to change some browser settings. So let's see what some other people did with this. Masato Kinugawa did something very similar. He found an endpoint on accounts.google.com where he could override the output encoding. So he set it to UTF-32, which is not supported in all browsers. It doesn't work in Firefox, it doesn't work in Internet Explorer. So if browsers get a page in an encoding they do not understand, they will still try to make sense of it. So they will decode that page using one of the encodings that they do understand, like UTF-8, for example. And this trick enabled a cross-site scripting vulnerability on this page in Internet Explorer. And here's what the cross-site scripting vector looked like. Yeah, that looks kind of weird, right? What is going on there? That's kind of crazy. Okay, so let's look at the hex dump. Now, UTF-32 was the fixed width encoding that we talked about. It takes 4 bytes to encode a single code point. So this is the first code point here, these 4 bytes. And yeah, so it's the for all symbol. It's a Unicode code point. But if you look at the ASCII representation on the right, or the UTF-8 representation, you get 3 null bytes and a double quote. The second code point is this one, Again, nothing really special, it just looks a little bit weird. But if you look at the UTF-8 representation, it's actually a closing bracket. So you see where this is going, right? I mean, depending on how you decode this document, you get a completely different payload. The only problem is that it's not a clean cross-site scripting vector. There are all these null bytes in between, and this causes Firefox to actually not execute the script at all. But it turns out that Internet Explorer just strips the null bytes. It kind of ignores them as if they weren't even there, leading to this, essentially. So there you have it. I thought this was a really clever exploit on accounts.google.com in Internet Explorer. One more example, Spotify. Does any of you use Spotify to listen to music, perhaps? Yeah, some people. OK. What you may not know is that they allow you to use almost any Unicode symbol in usernames, which is a good thing. They don't just limit you to the ASCII range. I think more services should be doing this. Unfortunately for Spotify, though, they had a very small bug in their code, which allowed attackers to quite easily take over someone else's account without even knowing the password. So let's say you wanted to take over the account of username Obama. What you could do is you could register an account with the same username, but using different lookalike Unicode symbols. In this case, I'm using Unicode modifier letters. So Spotify had a script that checked if the username already existed when you were trying to register it. But in this case, it would consider the two usernames to be different. After all, they are different strings, they use different code points, so this makes sense. Unfortunately, after logging into this brand new account that you created yourself with the password of your choice, they accidentally performed Unicode normalization, causing you to actually be logged into the real Obama account instead. So yeah, this was a pretty terrible bug on their end. Of course, they fixed it as soon as they found out about it, but it shows that Unicode normalization is quite powerful, and you should be really careful about when you apply it and when you don't. Another example of this is with GitHub. Now, GitHub doesn't just have the website, they also offer desktop applications for Windows and for Mac. And this is about a vulnerability in the Windows client. There's not really a lot of information available about it, but it shows that certain character translations were being done in the client. And this particular attacker figured out a Unicode character that was being translated into a double quote character. And then he could use that double quote character to break out of some shell command and basically do a shell injection attack, leading to a full-blown remote code execution exploit on Windows through the GitHub desktop client. So again, this is another problem caused by Unicode normalization. Now let's talk about JavaScript and JSON grammar for a little bit. Imagine an HTML page where a server-side script injects some user input into a single line comment into a script element. It also scripts ASCII new lines to prevent you from breaking out of the single line comment. So the question is this code safe? Well, let's take a look at the specification. The ECMAScript spec lists a number of line terminator characters, and the usual suspects like line feed and carriage return are there, but there's also these two guys, U plus 2028 and 2029, the line and paragraph separator code points. So with that in mind, if we go back to the previous example, now we see that this is in fact a cross-site scripting vulnerability. If the user input contains a line or a paragraph separator Unicode symbol, then anything following that character will not be part of the same line anymore according to JavaScript. So that part of the code will actually be executed. So this page is vulnerable to cross-site scripting. And that also means that JSON is not a subset of JavaScript, contrary to popular belief. So not all JSON formatted text is valid JavaScript code. So if you have a string containing JSON formatted data, you can use json.parse to unserialize it. Now, eval is often used as a fallback for older environments that don't have a native json.parse implementation yet. But depending on which characters the data contains, then running the data through eval might actually throw an error, whereas running the same data through json.parse would just work fine. And this difference between code paths that are being taken can be dangerous in some situations. Now, of course, you shouldn't be using eval in the first place to parse JSON or for any other reason, but there might be other situations in which you pass JSON formatted data to a JavaScript parser. So my advice would be, in general, always escape JSON formatted data before passing it to a JavaScript parser. I've actually built a tool that can be used for this. It's called JSAsk. It works in browsers, on Node.js. There's a command line interface as well. The source code is available on GitHub, and so you have literally no excuse not to start doing this right now. So here's how you would use it to create escaped JSON formatted data. So instead of using JSON.stringify, which would lead to strings that contain the raw, unescaped Unicode symbols, which could lead to these errors, you just use JSAsk with the JSON option set to true, and that way all these non-ASCII symbols that are special, they will be represented by an escape sequence in the data. So when you JSON parse the serialized results, the results will exactly be the same. So it will unserialize to exactly the same data, but it's just that the serialized representation is much safer this way. Now, another similar problem happens with surrogates. We talked about surrogate pairs before, where they combine together into a single astral symbol. And technically, surrogates cannot occur by themselves as lone surrogates. But in JavaScript strings or in JSON strings, lone surrogates are actually valid. The problem is that they're not valid according to Unicode. They're not valid code points by themselves. And UTF-8 encoders do not support lone surrogates either. So this can cause a number of problems. If you attempt to store JavaScript or JSON strings into a database that uses UTF-8, this might result in an error or even a crash in some cases. Of course, unless you escape the strings first. And this is not just some theoretical issue. The same thing, for example, goes for data that gets sent as a text payload over a WebSocket connection. WebSockets they only accept valid UTF-8 by design. So a UTF-8 encoded lone surrogate is technically invalid, and this would cause the client to be disconnected. So if the client is programmed in such a way that it automatically reconnects to try to start the connection again, and then it receives another invalid payload, then it will reconnect again and again. And essentially, if there is no logic to handle all these reconnection attempts, then this may lead to a very, very low bandwidth denial of service attack. You can just send the lone surrogate over and over again to the WebSocket connection to crash the server. And this was a real problem for the Socket.io Node.js package. Now, the advice is always escape JSON formatted data before passing it to a UTF-8 encoder. And again, you can use JSAsk for that, but we've already talked about that. So let's talk about some other vulnerabilities. Has anyone heard of Fabricator before? It's some project used by Facebook, as well as some other big companies. It's actually an open source project by Facebook itself, and it's what they use to manage their own software and their source code. It's very similar to GitHub. It hosts your Git repositories. It gives you a nice interface for issue management and code review and things like that. So let's say we are evil hackers and we want to get in here. We want to view the source code for Facebook.com. Of course we do. So we try to register for an account there. Well, Fabricator validates email addresses based on a whitelisted domain. So in Facebook's case, you will need to have an email address that ends with @fb.com. And of course, the only way to get such an address is to actually start working for Facebook. So unfortunately, we're kind of stuck here. We cannot create an account. But let's take a look at the code for Fabricator. It's written in PHP, and it stores its data in a MySQL database. Interesting. It also happens to use MySQL's UTF-8, which is not really UTF-8 after all. Yeah, so this opens up a number of possibilities for us, right? So instead of just entering our email address, evil@hacker.com, we can append some things. Like we can add an astral symbol, like the pile of poo, and then we can append @fb.com. So when we submit this form, the PHP code on the backend will validate if the email address ends with @fb.com, which it does. Then it will try to insert this value into the database. This will throw a warning, and the string will be truncated at the first astral symbol, and the result is that just our real email address is stored into the database. So after this, we can log in just fine. This vulnerability was discovered by Tom van Goetem, who's also present here today, so give him a high five if you meet him. And the same Tom van Goetem also found this 0-day in WordPress that led to remote code execution on some configurations. Now, this vulnerability is a little bit complicated. I'm going to try to simplify it a little bit so that I can explain it briefly. But I recommend checking out Tom's blog post about this for all the details. It's really good. So essentially, it was an object injection vulnerability in the WordPress core due to unsafe unserialization. But it's a little bit misleading to say that because there is not really anything that WordPress was doing wrong in their source code itself. So unsafe unserialization was not really the cause of the vulnerability. So this is a function that they're using called isSerialized. You see, whenever data is read from the database or stored into the database, it goes through this function because the data as retrieved from the database is usually a string. But it could be a string that represents a serialized PHP object like an array or a number or an instance of a class. And in that case, it needs to be unserialized before WordPress can actually use it, of course. And the same thing goes when saving data to the database. If the data is not just a string, you need to serialize it first. And that's why this function is being used all over the WordPress core. So there is a check here. If the last character is not a semicolon or a closing brace, then there is no way that the data is serialized. And again, there is nothing wrong with this code. All the assumptions that they're making here are absolutely valid. The only problem is that WordPress also made the assumption that if you store a piece of data into the database and then you retrieve the same piece of data from the database, that it is still exactly the same string. But as we saw earlier, there are cases when this doesn't really happen. And WordPress once again uses MySQL's UTF-8 by default, or it did for a very long time. And because of this, it is possible to save a string into the database with an astral symbol at the end, and this string would get truncated upon insertion. So basically, the value that ends up being compared on the back end before inserting it into the database is entirely different than what actually ends up into the database. And this is very dangerous. So here's what that will look like. So let's say you have access to a WordPress installation, but you just have a regular user account. You don't have any administrative rights or anything like that. So you could edit your profile, enter some serialized value in any of the fields, and then append an astral symbol there to trigger the vulnerability, and then update your profile. And when you reload the page, you will suddenly see that it no longer has the value that you put in there, but it actually says array now. And this is the vulnerability in the WordPress core itself. Now, how could you exploit this? Well, PHP has some magic methods like wakeup and destruct and toString that are automatically called when certain things happen to an instance object. So this means that we can construct a payload that unserializes into an instance of any class that we choose. So this could be any class in the WordPress core or any class that was added by some WordPress plugin that the user is using. So if one of these classes has a magic method that runs some code, we can now trigger execution of that code just by entering our payload into the WordPress administration interface. So you can see where this is going. This is how in some cases and with some very popular plugins that Tom found, you could actually achieve remote code execution on a WordPress installation. Kind of scary stuff. And this all happened in December 2013 when Tom published his blog post about it. At that time it was fixed already in WordPress. But just more recently, 2 years later, in December 2015, almost the same thing happened to Joomla. A remote code execution vulnerability was found, and this time it was not some white hat researcher that discovered this, it was someone who was actually using and exploiting this vulnerability in the wild. So there's a CVE for this, and it's kind of scary to even read this one sentence, because it says, arbitrary PHP code was executed via the HTTP user agent header, which sounds all kinds of terrible to me. But it actually works pretty much the same way as the WordPress exploit that Tom came up with. So if you're interested in the exact code, check out the link at the bottom here. But essentially, you would serialize a specially crafted object containing some PHP codes to be executed using one of the built-in Joomla classes. And then you would use that as the HTTP user agent header value with the pile of poo as a suffix. And that would trigger remote code execution just by making an HTTP request in any Joomla installation whatsoever. Kind of scary stuff. So another kind of big problem was a stored cross-site scripting vulnerability found in WordPress. So WordPress by default allows you to post comments to blog posts. And of course they sanitize these comments and they try to whitelist only certain HTML elements and certain attributes for each element to prevent cross-site scripting attacks. Now, this piece of HTML here, it may look a little bit weird, but it's actually completely legitimate. There's nothing wrong with this. This is not a cross-site scripting vector. It's just a queue element with a site attribute, and anything in between the quotes is just part of the attribute value. So nothing special is going on there. This is perfectly safe HTML. Now, what happens if you post this as a comment on WordPress, because they're using UTF-8? Well, the astral symbol will truncate the string. So after inserting this into the database and then reading it back out, after WordPress applied all its filters into the HTML output, you get something like this. So our perfectly harmless string has now suddenly turned into a cross-site scripting vector. So yeah, here's the full write-up about that. Another pretty big vulnerability happened in TweetDeck not too long ago. TweetDeck is owned by Twitter nowadays. It's available as a web app, but you can also download a browser plugin for Chrome or a native application for Mac or Windows. But no matter which of these options you're going for, it always runs in HTML, CSS, and JavaScript. The desktop apps, they're just a native wrapper around the web view. So a while ago, well, almost 2 years ago by now, they announced a new version with emoji support. And by that they mean that if you're using an emoji in your tweet, they will replace it with an image that represents that emoji. And then not too long later, they had to send out this tweet. So what happened in between these two tweets? Well, here's one thing that happened. Yeah, this looks like a very obvious cross-site scripting vulnerability. I mean, if this piece of code is executed, it's just classic JavaScript using jQuery library that actually clicks the retweet button below this tweet if you view this in TweetDeck. And the problem was, due to a vulnerability in TweetDeck, this would actually be executed. And you might think that little heart at the end of this tweet is kind of cute and it's just there for fun, but it's actually what made this whole vulnerability work. You see, TweetDeck was correctly performing HTML escaping before outputting the contents of a tweet into the HTML. But when they implemented their emoji feature, which essentially replaces the raw Unicode symbols with image elements, they added a subtle bug to the code, which basically unescaped the HTML before adding in the image. So that's why the little heart is really necessary to make this attack work. And needless to say, this tweet got plenty of retweets in a very short amount of time. It's essentially the very first worm on Twitter. Of course, this is relatively safe. I mean, the worst that happens is just it retweets a tweet, but other people were actually abusing this vulnerability to steal the contents for your direct messages and do other stuff like that. So yeah, it was kind of a terrible bug. Now, Yan Zhu published a more detailed analysis of the mistake that Twitter had made in their code. It's available on her blog, but essentially this is what the pseudocode would look like. So if the tweet contains emoji, you would replace the symbols with IMG tags and accidentally undo the HTML escaping that they did before. Yeah, honest mistake, I guess. Now, another example related to Twitter is this one. Twitter reflected some user input from URL parameters into HTTP headers. Now, to prevent HTTP header injection attacks, they blacklisted CR and LF characters, so you cannot input a new line and start a new header or start the response body if you wanted to. Now, the problem was their CR-LF filtering was kind of broken in a subtle way. If you were trying to use CR or LF directly, it would get stripped, so that didn't work. That's great job, Twitter. But there was a very straightforward bypass for this. See, if you bypassed the filter by using a Unicode symbol that had CR and LF code points in it, like OA or OD at the end, like this one, for example, it would work. It would bypass the filter as long as those byte values didn't occur in the UTF-8 encoding, which is being used for the URL encoded version. So here's an example of such a symbol. So 560A becomes E5988A in the URL, which bypasses the filter. And then when it gets to the server side, they try to turn this into an ASCII symbol somehow, I guess because of some libraries that they're using. And then this actually becomes the OA character, which is the CR. So essentially, you can then do the same trick and apply this to the LF character. And that allows you to put this together into this exploit. So the blue part is CR, the green part is LF, and then after that you can insert your own headers or even start a response body and take over the HTML response, do anything you want with it. And you might think, okay, this is just Twitter, it's just one company making this mistake. But a couple of months later, it was actually discovered that this was a problem also in Node.js itself. They have a very similar bug in their built-in HTTP response splitting protection. So they were doing something very similar to Twitter, really. They would filter CR or ALF directly, so that wouldn't work. But you could use the same characters or any other character with OA at the end in the code point, and it will also turn it into an ASCII value somehow. So a very easy way to bypass this is it's actually kind of the same issue, really. And this allows you to insert your own headers, redirect to other locations, or even overwrite the body if you wanted to. Now, I have many other examples that I would like to show, but I'm out of time here. So just remember, if you keep poking at your target for long enough, you might be able to turn bugs into exploits. And I personally think there's still a lot of Unicode-based bugs and exploits just waiting to be discovered, just based on this very simple information that I just shared with you. So go forth and spread piles of poo and fight all kinds of vulnerabilities. Thanks.